Hello everyone, my name is Shakya Jayakody. I'm from University of Central Florida. I will be presenting Peridot accelerating out of core GCN data reuse pattern and code design on GPU. Research problem. In aggregation and combination phase of graph convolution networks, GCN chain matrix multiplication is employed, which is a highly data and memory intensive. Inefficient memory or out of core memory issue pose a significant challenge on large GCN modules. This figure illustrates chain matrix multiplication within a graph convolution network during both aggregation and combination phase. During the combination phase of the GCN processing, each node features are updated based on its own features and aggregation features of its neighbors. This phase is computationally intensive for several reasons. Number one, the large volume of data. Graphs, especially those representing complex systems or large social networks, can consist of millions of nodes and edges. Handling such a volume of data requires efficient memory management to prevent bottleneck. Number two, high computation requirements. The combination phase involves matrix multiplication and the operations that are resource intensive. Efficient data handling ensures these operations and performs quickly, improve the overall speed of the learning process. Number three, dynamic data access pattern. Unlike image or text, graph data has irregular access patterns that can lead to inefficient use of cache and memory bandwidth. Techniques like GPUDirect Storage (GDS) can mitigate this inefficiency by optimizing how data is transferred and accessed, directly impacting the performance of the combination phase. Number four, scalability. As models and data grow, the needs for scalable solution become critical. Efficient data handling technique issue that increase in graph size and complexity do not linearly increase the computational cost, making it feasible to tackle the large problem of within the available hardware. Background on GPUDirect Storage (GDS). The left side of the figure displays the traditional data transfer method using CUDA memcopy, which move data from secondary storage to the GPU. The right side illustrates the NVIDIA GPUDirect Storage, which bypass the CPU bounce buffer to directly transfer data from secondary storage to the GPU. Offers several advantages. Number one, reduce the latency. By eliminating the detour throughput CPU memory, GDS significantly cut down the time it takes for data to reach the GPU. This is crucial for applications requiring real-time processing and analysis. Number two, increased throughput. Direct data path allow for higher data throughput rate. This is benefit in environments where large volume of data needs to be processed quickly, such as in video processing or complex simulation. Number three, enhance scalability. GDS make it easier to scale application by removing the memory bottleneck associated with large-scale data transfer between storage and GPUs. This is essential for expanding the capability of system without compromising on performance. Number four, improve resource utilization. By reducing the load on the CPU and its memory, other processors can use these resources more effectively, leading to overall improvement systems efficiently. These are some of the disadvantages using GDS. Sending small data. GDS is optimized for high throughput and large transfer, so sending many small packets individually can lead to inefficiencies. Initialization overhead. Setting up a direct data path between the storage and the GPU in GDS can result in higher relative latency for small data packets due to the setup overhead. Our contribution. Automatic data compression technique. This technique utilizes the operator hints to detect the sparsity based on the tiered memory hierarchy and select the appropriate sparse matrix compression algorithm for matrix A and matrix B, respectively. Automatic data transfer technique. This method selects the low latency zero copy path through a GPU direct storage approach. It's enable direct loading of sparse matrices to the GPU, bypassing the CPU to minimize the CPU involvement. Additionally, verify whether the CPU is used to compress the matrix before transfer. Metadata and data coupling technique. This approach is designed for out-of-core sparse general matrix multiplication computation to optimize the sparse allocation within a tiered memory system, including high bandwidth memory, GDS, and host DRAM. Peridot, integrating GDS with GCNs and our solution for efficient memory management. Figure 2, Peridot memory utilization. Initially, all the GCN data, including the adjacency matrix in CSR format and the weight matrices in CSC format, are stored on NVMe. For out-of-core sparse matrix multiplication executed on the GPU, GPUDirect Storage facilitates the transfer of the CSC formatted weight matrix B to the GPU. Meanwhile, the adjacency matrix data is transferred to DRAM and to the GPU memory. Here, row-wise metadata for the CSR format adjacency matrix A is stored as a tile on the GPU to be readily accessed for computation. Space is reserved in DRAM memory for hot data and metadata, which include converting adjacency matrix data CSR-A into partial metadata and processing the resulting data. Peridot hierarchical memory management system offers multiple advantages. Number 1. Reduce DRAM usage. Minimize DRAM consumption crucial for accelerating chain matrix multiplication processes. Number 2. Lower latency. Utilize GDS for large GCN data transfer, significantly reduce the latency. Number 3. CPU offloading. By offloading data transfer tasks to GDS, Peridot efficiently free up CPU resources for other processors. Number 4. Optimize memory utilization. Systematic exploration and optimization of memory allocation for CSR-A and CSC-B format ensure maximal memory efficiency. The performance of Peridot was evaluated using undirect graph suite of graph dataset from the suite sparse matrix collection detailed in Table 1, which provide a diverse set of real-world graph datasets. The performance comparison Table 2 clearly showed the capability of the Peridot system both with and without GDS against a traditional baseline. This analysis focused on two key matrices, bandwidth and latency, which are critical for assessing the efficiency of the data handling technique in GCN. The results demonstrate the Peridot significantly enhanced the bandwidth across all the dataset when compared to the baseline configuration. Conclusion. Number 1. Performance improvement. The integration of advanced data transfer techniques and memory management strategies in Peridot leads to substantial improvement in processing large-scale graph data. Number 2. Increased bandwidth and reduced latency. Demonstrate across the multiple datasets, highlighting the efficiency of system. Number 3. Effective use of GDS. The application of GDS technology within Peridot show its capability to handle intensive data transfer effectively. Number 4. Addressing key challenges. Specifically target and overcome the issues of memory limitation and data transfer delay, which have traditionally hindered the scalability of graph processing application. These are some of the related work. Acknowledgement. This work was sponsored in part of the US National Science Foundation. Reference.